Hello, and welcome to this talk about the Royal Society of Chemistry's experience of integrating ChemAxon NMR predictor into one of our database products, MarinLit. My name is Dr. David Sharpe, and I'm a product manager here at the Royal Society of Chemistry, specialising in the databases portfolio. So, just to explain a little bit about the Royal Society of Chemistry, as an organisation, we're over 180 years old. And we're many different things, but we're partly a society non-for-profit publisher, publishing over 40 peer-reviewed journals. As well as that, we're a membership organisation with members all over the world, and we're the professional body for chemists in the United Kingdom. And we promote the chemical sciences and support members of the chemical sciences community. So the database I'm going to talk to you about today is called MarinLit. It's a database of marine natural products. So we have a curation team who read through all the literature, and they look for reports of new marine natural products or revised structures. And they go through and they add all of the citations and the chemical structures as well. So it's a really highly used resource in the marine natural products community. And it's really important that all the data is updated as soon as possible. So MarinLit itself is over 40 years old, but it's only been part of the Royal Society of Chemistry portfolio for the last 7 years. So the version of the website and the workbench that we had was basically the first iteration that we produced. And we kind of realized that we wanted to change things up a bit. So we wanted to improve the user experience and make the site more responsive, so that it would work on desktops, mobile devices, etc. And we wanted to improve the quality of the data, and also change some of the processes that we used in actually creating the data. So, for example, with the NMR prediction data that we had before, rather than that being generated as soon as a new compound was added to the database, it was actually an asynchronous process where we exported out the compounds, generated the predicted NMR properties, and then wrote that data back in. And that wasn't how we wanted to continue creating the data set. In addition to that, we're in the process of moving many of our websites and applications into a cloud hosting service. And so when we did this redesign, we really wanted to make sure that we took advantage of all the benefits of being in the cloud. So this slide here is just a selection of a few structures from the MarinLit database. And what I want to highlight here is that we have some very big structures, and obviously some smaller ones as well, but also there's quite a lot of them that are quite highly functionalized, for instance, sugars, and then a lot of stereochemical information as well. And it was certainly in the forefront of my mind when we're looking for new production software, was that in our existing set of 37,000 structures, we would possibly have some quite challenging chemical structures to process, and that it could be difficult to find a tool that might be able to do all of those, predict information for all of those. Now, in terms of the actual data that we use in MarinLit, there are basically two kinds of usage. One, we have the predicted NMR data displayed on the compound records. So that's both as a tabular view, but also we have some illustrative images of what the spectra might appear a bit like. And I'll show you some of that in a second. And we also have what's termed sort of a dereplication tool. It's a very sort of advanced set of searches that can be built together, And one of the options is to search based on chemical shift from the NMR spectra. And I'll show that again in a second. So just looking at here, this is the record from the record for sonodron C. And what you might notice is we don't actually annotate each carbon and proton environment with the chemical shifts. But what is very important is that we correlate the carbon NMR shift with the proton NMR shift of any attached protons. So just taking that first row in the table, we can see there's a carbon or carbons with chemical shift at 128.9 ppm, and it has one attached proton to it, and that has a chemical shift of 7.51 ppm in the proton NMR. And this is throughout the data that we're going to talk about today, a really important feature. So this is another way we represent the data on the chemical record. So an exemplar of what the carbon NMR spectrum might look like. And here you can see we've colored the peaks. So blue for quaternary carbons, red for CHs, green is CH2, and methyls are black. And again, this relies on having the information about how many protons are attached to each carbon. And similarly, this can be expanded to correlate all the data together in this prediction of what a HSQC spectrum might look like for this compound. And again, we're able to layer on that same coloring of red for CH, CH2 green, and black for methyl. So we're definitely relying a lot on this data. Now, just before I go through the requirements, I'll just show you how we were doing the dereplication. So this refers to sort of the way that you can build up searches. So it's possible for you to put in an exact mass or a molecular formula, select functional groups, but also put in NMR data. So if I just put in a few example NMR shifts and then specify that that should have one attached proton, add another one here, 9. So, then put a proton shift in here as well. So, okay. So what you might have seen is this number up here is updated. So it went from all 37,000 compounds in the database to now we've filtered down to 1,700 compounds approximately. And we could go on adding more features to the NMR data or adding other parameters to narrow down to finding matches across the Marinlet database. And that's a very useful feature for natural products chemists. So from everything that I've just shown you there, we built up a set of requirements of what we needed from NMR prediction software. And that was, we must be able to reliably handle and process complex chemical structures. We ideally wanted the process to work by us passing in a mol file and getting out the data. And then it was really key that with the output data, we would be able to do this correlation between the carbon NMR shifts and any associated proton NMR shifts, and be able to have the data in the right format that we would be able to generate all of those data sets that I just showed you and provide the searching that I just demonstrated. In addition to that, we really wanted to make sure that it would work within a cloud environment because we're building all our data processing within the cloud as well. And a final point was, while in many cases we might only be generating predictions for a single chemical structure, we were very aware that especially in the early development phases, we might want the ability to regenerate all the data at once. and that could be a useful feature in the future. So we really wanted that ability to trigger the generation to have either single or batch prediction. So we went out and started to look at the potential options, and our data team tried the desktop version of the ChemAxon prediction software, and from their test they were satisfied that the prediction algorithm would work really well with the data that we had and generate the types of information we needed. So then, having selected ChemAxon, we came to the challenge of how this might then fit into our new cloud-first workflow. And actually, we had some really good news, which was that ChemAxon had an ability to package the prediction software as a Lambda, which is just for those who don't know, it's just a kind of module that you can have in many cloud platforms. It usually takes an event and some data, does some processing, and then it then might trigger another event and output some data. So that was perfect for what we needed, and we were already using quite a lot of Lambdas. And so by after having received the ChemAxon prediction Lambda, we were able to integrate it within a couple of hours and start triggering the prediction of data based upon saving a mol file, which was really good. It was just so easy to get that all working together. We did have a point where we realized that to get the data we needed, the proton and carbon NMR data would need to be changed slightly, and so we talked to the ChemAxon's calculator team, and they were able to help us and actually revise the Lambda so that we'd get out exactly the kind of data we'd need, with the correlation of the proton NMR and the carbon NMR shifts. And in fact, this got rid of the need to do lots of post-processing after the data was generated, so that was really useful too. And so we've now been running these Lambdas to generate the proton and carbon NMR data for 37,000 structures, and we've done this quite regularly and repeatedly. And we've not particularly optimized this, but in general, when we rerun the whole set, it takes us less than 2 hours to generate all of those predictions that we need. And as that was as fast as we needed it to be, we haven't tried to reduce that time. And if we just trigger the generation of predictive properties for one compound, then that really just takes a few seconds to run and generate the data we need and write it back into the database. So that's great as well. So really, just to sort of round off this talk, I've actually shown you the new site that we produced, which is powered by the data that we generated using the ChemAxon NMR software, and you saw the pages with all that, the data rendered there. So it worked really well for what we needed to do and gave us the data that we needed and the quality we needed. The fact that we're able to get the prediction algorithm packaged in a Lambda made life really easy for us. We didn't have to do any difficult integration in our cloud setup. And it's been really fast for us. So as I said, being able to regenerate 37,000 predictions in a matter of hours is really good. And so, we're very happy. And now I'll just ask if anyone has any questions. Thanks for your time.